Yes.
जी सर.
So here we are starting with the force vibration, the force vibration response of a system. Previously you have seen that we are not much interested in the right hand side PT because it was 0 and we were just noting the free vibration response. Now we are also interested here that if the force is also present and force is also time dependent. Now we are touching the thing that the earthquake loading, for example, when acting on the structure is also a time dependent. So this is linked with that. That if the force is not 0, the right hand side of the equation we have in following mu plus cu plus ku, m into acceleration plus c into velocity and stiffness into displacement was 0 equal to 0, but now the pt will be present. This pt can be of short duration, it can be of long duration. Now we will see the response of this force. So the response of a system subjected to a short duration force is also of short duration, called the transient response. Damping in the system causes vibration to decay and the system returns to the rest after a while. This type of response may be critical because of the low cycle fatigue. So due to the fatigue and due to the other effects, the resonance can be generated because now there is not only the frequency of a system, but there is also frequency of a force. So we have to see that there are two types of response in this case, force vibration. One is called as transient response, is due to the initial condition and present only at the beginning and decay due to the damping. And steady state response lasts as long as the exciting force remains. So transient is the system response that you was previously studying. The steady state response is due to the force, that what is the effect of the force in the system and what was the previously studied the damping system response, free vibration response. That is a kind of a transient response. And the failure here you will see some new terminologies also, like resonance, this frequency beta value, the ratio of the frequency of the system, the ratio of the frequency and frequency of the applied loadings. So there are some other parameters will also be involved in this case, forced vibration. Because the load here you have this graph also that you can see here, graph of a force that is plotted between the PT. PT can be generally written as we can represent with the different units also, but generally it will be written like PT. The force is P, not only the one value. P naught is the magnitude, or it can be any, and because this force is a time dependent, so sine function is used, sine of ohm t or omega t. So PT is the P naught sine of omega t, or sometime it can be P naught cos of omega t. It means that initially we are starting with the regular function of a force. Force is a function of the time. Time is varying, and here you can see the force function. P is equal to sine omega t, where P naught is the amplitude of the force. जो P naught है वो maximum इसका amplitude है, and omega is the frequency of the vibrating force जो इसकी frequency है force की. Force is also the frequency, so that's why that is represented by, क्योंकि omega हम उसके लिए कर रहे हैं तो इधर हम बुक में different symbols हैं, तो don't confuse with the symbol. Here we are also represented it with the omega, but inverted omega, or sometimes it's written as the ohm in the electrical engineering. So example is the unbalanced rotating machine. Unbalanced rotating machine hai, that is also example of the harmonic force vibration. The study of the harmonic force vibration, while useful by itself, also provided insight into the nature of the force vibration of a more general type. ये फोर्स वाइब्रेशन के बारे में ये काफ़ी एक्सप्लेन इसमें हम कर सकते हैं। तो इसके भी ये इस तरह प्रूफ है, दो तरह के सोल्यूशन हो, और फाइनली जो सोल्यूशन होगा, बिकॉज these things are already covered in undergrad, so we are not really interested in the final solution and response mainly. Individual आप सारे प्रूफ अगर देखेंगे तो the procedure for computing the constant and the different parameters which are involved in the proof are same, and finally the response, differentiating the response is very important कि कौन सा damped system का है, undamped system का है. So please note down the response for all the cases, जितने भी different parameters and formulas हैं, you should try to write it separately with clear headings, that this is the expression for the response of the undamped system, this is for the damped system. So you must be very much clear about that. So here also, if you see the undamped harmonic vibration, first is the undamped force vibration is also of two types. We first resolve the undamped proof, and then we resolve the damped harmonic vibration response. So C factor is 0 here. C is 0 in this case. There is no damping coefficient is 0. And only the stiffness is present. And only the, of course, the mass of the system will always present, but force is not 0. Force which is present is on the right hand side will always remain present. So the solution of the equation of the motion is made with two. Now we have to make the solution with two parts. Where we don't involve the force, and particular solution that give the steady state. जैसे मैंने आपको दो, I have told you about the two responses. One response is a steady state response and one response is a transient response. So this gives the transient response solution आप करेंगे, that previously we studied, that how the system is, and due to the force, what is the effect on the system, that is a particular solution or particular, or this is also called as the steady state response. So the equations are same, only the one force parameter is added. So complementary solution remains same as that was used for the undamped free vibration, A cos omega t, P cos omega t. And particular solution now we solve UP, the response of our system due to the force is G sine of ohm t. And now by putting the value of the derivative, second derivative is Scalalia, then taking the U value, putting the U also, it equal to P naught sine of ohm t, putting the value of that, and then G is equal to this one, P naught over K minus M omega square. And now summing the response. In this case, we have to sum the response of the particular solution and complementary solution. We have to add the response. This response was due to the system response, and this is the added response due to the force. Now to determine the initial conditions, again the same thing, that first you take the U value, take the derivative and put it equal to initial condition U naught, and then take the derivative and take the initial condition as V naught. So A U naught is determined cos of omega t. So U naught is computed as equal to this one, because this is also 0 initial at time 0. So U is equal to U naught is equal to A only. A is equal to U naught, and second case is the V naught we again take the derivative of that equations and put down the time equal to 0. So cos of sine of 0 is 0 and this become 1, and then we determine the value of the b and v naught from this one. So now putting the value of the a and the b is determined from this equation, a determined from that equations, and now putting back into this last equation, we can determine the response of the system. This is the response v naught over omega, and this is the value of the b. So this response is a transient response. This will change slightly because this time the force was also present. So previously it was just like u naught cos omega t plus v naught over omega sin omega t, but now this factor is also added in the response. And this response is the steady state response, the force response. We put down the value because the final equation was this one, p naught over k minus m omega square. So that is written as it is. And now we have two response. The first two parts are of the transient response, and the last is a steady state response. So this response is obtained, and further simplifying it and collecting the similar terms. So finally you get this equation, and further simplifying it because we divide it by this ohm symbol, let's say omega for the force, omega force divided by the omega of the system. This omega is of the structural system, and this omega ohm is for the force system. So actually you say that this divided by omega, this is written here also, is beta. Beta is the ratios of the frequencies. So frequency of the force is ohm and frequency of the system is omega. So you just replace, divide whole term by beta, इसको आप omega से divide कर दें, dividing the term by omega, and we can write it is in this form, k p naught over k into 1 minus 1 over beta square. Because this m was there, so we divide m is equal to k over m जो है that को जो है we can replace by k, and we can then the k over omega, and k over m is omega. So from that we can determine the m also, and replacing that value we can determine that it will be equal to beta square. So now the final response of the system with the force will become this. This response of the system is in case when the force is present. Now you have all the values are available. U naught, initial displacement, initial velocity, omega is the natural frequency of the system, p naught is the amplitude of the force, this omega ohm is equal to this is the representation of the frequency of the force. Beta is the ratios of the frequency. This is because you know when the beta is 1, then the things are quite complicated for the structures. It become resonance case when the beta becomes 1, when the frequency of the force and the frequency of the system equal to are same. So then the system will beta will be 1. So this is the ratios of the frequencies. So this system response we studied about the undamped harmonic response. Now we have the multiple things we can extract from this equation. How? For example, what is the particular solution? The last one, 1 minus beta square p naught over k. So this is the solution which was for the transient response. So we said the dynamic load factor is the ratio of the maximum dynamic deflection steady state में जो आ रही है to the static deflection. What is the static deflection? Simply load over stiffness. And what is the dynamic deflection? That is equal to up, that is p naught over k 1 over 1 minus beta square sine omega t. So ratio of these two, up over u static, this is the dynamic magnification factor. इसका आंसर आता है 1 over 1 minus beta square into sine ओमेगा टी। तो ये डायनेमिक लोड फैक्टर है, यानी कि दिस इज द रेशियो ऑफ द डिफ्लेक्शन जब आपका फोर्स सिर्फ अप्लाई हो रही है, एंड in that case when the force was varying up and u static when the force was not varying, I mean not changing with this, iska ratio, that is dynamic load factor. The coefficient of the dynamic load factor जो 1/1 minus beta square है, because sin omega t तो उसका time के साथ varying response है. The coefficient of the dynamic load factor is called as the dynamic magnification factor. So 1/1 minus beta square, the coefficient of the amplitude इसको हम कहेंगे of the dynamic load factor, which is 1/1 minus beta square, is called dynamic magnification factor and is given by 1/1 minus beta square. For small value of beta, अगर आप small कर दें values को, अगर आप plot करें AD और beta को, small के साथ क्या होगा? It will be AD will be 1 and for the beta जैसे जैसे 1 हो जाएगा तो it will be infinity. It means that the dynamic magnification factor play very important role. ये undamped का ये response है, जिसमें आपका C 0 था, तो AD the dynamic, क्योंकि damped के लिए भी आप देखेंगे that will be a bit different. So the response of the system, amplitude जो आ रहा है आपका, amplitude of the dynamic factor AD versus beta when you plot. When the beta is less than 1, the black color curve is shown. It means that as you are increasing the beta but less than 1, the amplitude is increasing. And when you again increase the value of the beta not 1, 1 पे ये infinity में चला जाता है dynamic magnification factor, but larger than 1 पे फिर क्या होगा? That it is in negative में ये increase करेगा. But as you are further increasing the जितना आप away होते जाते हैं ratio of the दोनों की फ्रीक्वेंसी से, यू आर रिड्यूसिंग द एम्पलीट्यूड. जितना दूर होती जाती है फ्रीक्वेंसी ऑफ द सिस्टम एंड फ्रीक्वेंसी ऑफ द फोर्स, तो आप देखते हैं कि ये क्लोज टू द जीरो आता जाता है डायनामिक मैग्निफिकेशन फैक्टर. जैसे जैसे आप ब्लैक कलर भी देखते हैं, बट एज यू आर एम्पलीफिकेशन इज मोर. तो फॉर स्मॉल वैल्यू ऑफ द बीटा अगर आप बात करें, AD इज अप्रोचिंग 1, स्मॉल पे AD ये 1 पे चला गया. इधर आप अगर देखें ना, अगर आप बात तो फिर ये 0 पे जाता है जब ज्यादा है, और 1 पे अगर आ जाता है, स्मॉल वैल्यू रेशियो जो है इसकी बीटा की भी, बीटा इज आल्सो 1, तो देन इट बिकम रेजोनेंस 1. इसको हम क्या कहते हैं? इन्फिनिटली लार्ज आपका रिस्पांस होता है, एंड दिस कंडीशन व्हेन द बीटा इज अप्रोचिंग टू 1 इज कॉल्ड एज द रेजोनेंस. We always try for our structure, the frequency of the system should not match with the frequency of the applied loading. This condition is called as the resonance. And at this condition, the dynamic magnification factors becomes too large. ये इसका फिर response है. Generally, if you plot the deflection versus time, deflection of the system versus time, जैसे जैसे this is shown with the green color, red color is shown for the beta जब less than 1 था, beta जब 2 है तो you can see कि deflection further कम होती जाती है. तो when the beta is less than 1, the deflection is still remains more. It's when the beta is approaching larger values, the deflection is further diminishing. Now you can we have already proved that relation, the response of the system or the undamped. Simple case when u naught and v naught अगर 0 आप कर दें initially, the response will be like that, putting the values, and this is just modified. And when you put the beta 1, यानी कि resonance पे अब हम बात कर रहे हैं, that what happens when you are tending towards the resonance response. कैसे आप निकाल सकते हैं resonance response? कि आप बीटा को 1 कर दें, बीटा को 1 पुट कर दें, तो यू कैन सी कि वो तो फिर सारी वैल्यू इन्फिनिटी में चला जाएगा. सो सॉल्विंग इट विल बी डिफरेंट. सो देयरफॉर यू विल अप्लाई द एल हॉस्पिटल्स रूल. एल हॉस्पिटल्स रूल को हम अप्लाई करेंगे to find out this the response. Resonance पे response के लिए ना आपको limits वाला you have to put down the limit value problem, because नहीं तो ये infinity आ जाता है आंसर. So you will use the limit value, limit beta is 1, and then you can write down, ये आपने formula पढ़ा है कि it's equal to the L'Hospital's rule, in where you can write down the equation this into this form, and then solving it you can determine the response at resonance. So in this way you can also solve the response by this equation. You can get the response by the resonance just by putting the beta equal to 1, but putting the limit state problem, then we can solve this. Now what is the response of the at the resonance? The peak response of the system is obtained at the resonance. So this was the resonant response that you have seen that the resonance response is obtained like that. For the system, and for the simple case, and we apply the rule, and then this is basically the resonance response. You can put the value of the time, the omega and p naught stiffness, and we can get the resonance response. If you plot this response as a function of the time, you see that at resonance the system amplitude is uncontrolled. It's too high that it is not controllable. You can see the response is a periodic with period 2 pi over omega के साथ आप increase करते जाएं हर बार time को. U was this, then you take the derivative of this. This is the, and then you take that different values. So it is just becoming the omega t every time that when we put down the values. So difference between the two successive जो peaks है वो कितना बन जाता है? It's too high. It's deflection time pi p naught over k. अगर आप ये सारे निकालें and difference निकालें between the two successive peaks, it's too much. It's like p naught over k into pi. If you take the difference, the first में or second में, the first and the second one response by increasing. So it's this is the response of a system, undamped system, in case of the resonance. तो ये आपका undamped system था harmonic motion का, and this was the response for the resonance. The next part is the damped harmonic vibrations के damped अगर आप C भी ले आए तो उन equations में क्या change आती है? तो आपने you will see that some changings are there, of course, because now what is happening that damping is affecting the response. You will see that the damping वाले expressions आ जाएंगे यहाँ पे. Not it is an undamped free vibration नहीं होगा, damped free vibration response होगा. That is the जो दो तरह के आपको response बताए थे, transient and the complementary response. So there will be a steady state response due to the force, and the transient response also of the system. So you see that in case of the damped harmonic vibrations, the C is not 0, and you can write down the equation in the same way, but now the solution of the equation will be like that, and you have to determine the G1 and the G2 values. And on putting in equation 1 the derivative, taking the derivative first and then first derivative, second derivative, the same procedure, and then putting the condition u naught, initial condition at time 0, and you can find out all the parameters, and then putting back the G1 and G2 value. This equation is obtained. So here this is a solution G1 and G2. The particular solution is this one. And the complementary solution, which was due to the damped vibration, ये जो पहले हमने पढ़ा in the damped system, e raised to power minus zeta omega t, a cos of omega t. This is a particular solution. Complementary जो आपका है, and the particular solution due to the force is this one, and the solution due to the damped vibration of the system is this one. Now we can sum up these two responses, steady state response and the transient response. इनको हम sum कर दें. This is due to the e raised to power minus zeta omega t, a cos, and a and b हमने determine कर लें. How? By taking the derivative of u and then putting the first 0 u0 and then taking the u dot t0, we can find out the a and the b constant. It's quite lengthy, but finally we need that to put down the equation, and then this equation number is, let's say, 5. The complete solution of the damped system, a and b are determined in equation number 6, 7, and then your total transient response now will be, if you put the a and the b value, ये आपका transient response आएगा. It's quite lengthy, and you have to, this is written in circle, and the total, when you write down this, ये दोनों आ गए, complementary response, total transient response and steady state response. Now if you plot these response, undamped harmonic response, if you plot this response, you see that the total response जो है, that is for the undamped, ये ऐसे चलेगा, because there was no damping, तो ये कम नहीं हो रहा था. जो total आपका response था, damping was not there, so this keep on vibrating like that. In steady state जो force का effect था, that was like that. Force or steady state response is shown in the pink color. But when you go to the damped system, you see the total response is with the time due to the damping, the vibration जो आपकी है वो change हो रही है, क्योंकि force भी apply हो रही है ना, तो system is vibrating. So the transient response, steady state response is a pink color, the total response is in the blue color. So the total response, initially there are the more vibrations. Actually अगर real में आप plot करें, so you can see by putting the values and try to practice in this also in the MATLAB, you can see this response of the system. So damped harmonic vibration, the transient response will decay with the time. आपने देखा है कि जो response है transient, that is decaying with the time, and the vibrations are diminished because of the damping effect. So finally the steady state response of a damped harmonic vibration जो है, it can be written, ये आप अगर simple लिखना चाह रहे हैं steady state का, it will be like that, 9 equation, where rho is equal to this one, rho इसके बराबर. तो ये है आपका response, steady state response, equation number 9, and equation number 8 is a transient response. So transient and the steady state response, where phase angle in case of the steady state response is equal to 2 zeta beta to 1 minus beta square. तो ये आपके damped के सारे response हैं. तो ये number 9 and 8 ये separate responses हैं, and ये रो अगर आप इसको simple कर लें, तो response is more or less very close to that system when there was no force vibration, but of course the rho value अंदर फोर्स आ गई है. So there is the amplitude values have been changed. Now if you extract the dynamic magnification factor and the amplification factors, then you will see some difference. Now if you take the dynamic load factor, जो पहले भी आपने पढ़ा, ratio of the dynamic to the static displacement. Dynamic to the static displacement. What was that? In the previous case, it was different when there was undamped, but in case of the damped, when you take the ratio, you get this value. The dynamic response load factor is equal to this one. This is 1 over 1 minus beta. Beta is the frequencies ratio. Zeta is the damping ratio. So you can have all the values now, and this is the dynamic. And इसके जो coefficient है वो क्या बनेगा? Amplitude of the dynamic load factor. The amplitude of the dynamic load factor का इसको dynamic magnification factor कहते हैं. So that is AD. AD is like that. And now if you plot the graph between the AD and frequency ratio, this graph is different than the undamped system. Undamped, that was you see the side, this curve was there, and then there was like this kind of case. But here the response of the system, it's going like there, and then the response is not available because the values of the frequency is matching. One is the resonance conditions, and then again the response start, and this is the case when the frequency ratio is larger than 1. This is the amplification factor. This is the dynamic to the static displacement. This is the dynamic load factor. And now if you plot the relation between the frequency ratio and the amplification, and you will see this one response. You can see the relation between the amplification and the this one is 1 over 2 zeta, 1 minus zeta square. If we get the relationship between the beta and the AD. इसको derivate कर लेना के साथ, you can put it equal to 0. Maxima लेने के लिए एक अब आपका maxima आएगा amplification. So maximum amplification factor can be determined by this one. So these are actually very interesting because these are interlinked, and you can put down the different values, and the formulas are not much complicated when final form is simple hai. And if you want to plot the frequency ratio versus the phase angle, you see कि frequency ratio के बाद the phase angle is 90 at the frequency ratio 1, because this is the formula for the damped harmonic vibration at resonance when beta is equal to 1. All the curves passes through the same point, same phase angle. For beta less than 1, phase angle is less than 90. For beta larger than 1, phase angle is between 90 to 180. So here आप देखें कि phase angle का will change the ratio behavior of the phase angle as a function of the frequency ratio. That after the 90 degree, the phase angle is changing like that. For undamped system, the steady state response is in phase phi 0 with the exciting force when beta is less than 1. ये जो blue color line है ये undamped की है. Angle remains 0, undamped until the frequency ratio, then suddenly it is go to 180 for beta. ये undamped है. But for the damped system, these curves are shown. And for different value of the zeta, यानी कि different damping ratio के लिए, for these curves are changing. Like for the 0.5, the brown color is shown. For value of the 0.2, this pink color is shown. 0 के लिए जो है ये blue color is shown. So 0 is basically the mean that there is undamped system. Undamped के लिए ये straight or simple. This is the relation between the phase angle and the frequency ratio. अब resonance response damped system के लिए simply you put the beta 1 put कर दें तो steady state response आ जाएगा, and by putting the beta 1 transient response आ जाएगा. So forced response, steady state and the transient response. In the initial phase the transient response कर देगा. When the transient response diminish, जब ये transient finish हो जाएगा, then the system vibrate with the exciting force but lagging by 90 degree. ये जो है इसका the system will remain with the exciting force. For small damping, the total response, अगर आपकी damping small हो, by summing these two equations and putting the zeta value small इसमें जो zeta, you can ignore the higher terms of the zeta, and this can be written in this form. This is the response of the system at the damping. So when you plot this response together, you can see that steady state amplification, this is the envelope for the resonance, and for the different damping, this you see that the resonance is increasing and increasing, and as the number of cycles, certain cycles के पास the amplitude ratio become constant. Certain cycle के बाद the amplitude ratio becomes constant. So this was the response of the effect of the resonance for the damped systems. So this one with the continuation of that, if you plot the response, अब तीन तरह के response है ना, displacement response, velocity response, and the acceleration response. So there are three types of response, and we can have we call it as a RD, RV, and RA. And how can we UT is already known. The response of the system is this one. And by taking the ratio of the displacement response, dividing it, I mean by the deflection, P naught over K. And now we say this, ये जो बनना है, we say it as RD. ये जो the coefficient of basically the coefficient of the functions for the displacement response is the displacement response factor RD, and then you derivate it and then take this coefficient, this is RB, then you second time derivative and then take this function, that become the RV. These are interrelated. So UT was this one for the damped system, and then you say okay, UT over P naught K, bring it on the left hand side. Now RD will be equal to, the RD is 1 over 1 minus this part, the coefficient of this sine omega t minus phi is RD, the displacement response factor. Now you take the derivative of the UT. So you take a derivative and solve it. Again you put the this P naught over Km on the left hand side, this factor on the here, and then you this response, which is the basically the left part of the angle RD into the rho cos of omega t. So this factor is called as RD into omega into m over k. This become the RV value. And again second derivative is taken and it is simplified, and this part is basically now called as the RA value. तो ये कैसे लिंक है? RD is basically equal to beta RD is equal to RV, and RV is RA over beta. These are linked with each other, and when you plot the RD displacement response factor as a function of the beta for different damping ratio, you get this response. When you plot the dynamic response factors ही हैं, लेकिन ये dynamic response factors अब further उसको 3 parts में कर दिए हैं, displacement, velocity and acceleration. And when you plot the velocity response factor, you get this kind of the same values के लिए. When you get the acceleration response, it means that you can combine all these. इनको combine भी हम कर सकते हैं, because in the dynamic analysis 3 things are interlinked: displacement, velocity and acceleration. All the time these can be interlinked in such a way. Now we can combine it, and there is one special plot. इसको हम कहते हैं 4-way logarithmic plot. इसको we can plot all the functions. How? Y-axis पे velocity, x पे frequency ratio beta, and we can, because all these 3 values are interlinked, you see from this relation, so we can have one another line here. This line is a RD value, this is RV value on the regular y-axis, and inside जो axis है, this is a RA value. ये भी 90-degree angle है. So now you can, if you compute the value, तो different आप निकालते हैं. This idea will go to the response spectra. आगे जो हम पढ़ेंगे ना, so the same idea. And when you plot this value, RD value, displacement response factor, and you can get that. You can put down the value, and finally जो 3 ग्राफ हैं उनको आप सिंगल में भी रिप्रेजेंट कर सकते हैं. All these 3 graphs can be representing on the single, because RD, RA and RV can be represented, and this is available. This graph is available in the book, in the internet, and you can work on the computing the RD, RV and RA value and plot a single graph value also. So these was basically getting an idea of the relationship between the displacement response and velocity response and the acceleration response. And what happened at the one value पे आपका all response are peak. Displacement देख लें, velocity response, acceleration response. That point is called as the resonance. Now you can, the frequency at which the larger response occur, उसको हम resonance कहेंगे. Steady state displacement, velocity and acceleration response. ये steady state system जो है इसका all responses are there. So what is the at resonance? What is the frequency ratio at resonance? Displacement resonance frequency ratio is this one. Velocity resonance frequency ratio is this one, and acceleration resonance frequency ratio is this one. हर केस पे ना resonance frequency ratio बताई गई. So displacement response factor, finally it can be written like that. Velocity response factor, ये formula है. Acceleration response factor is this. I told you already that these are interlinked with each other. ये resonant frequencies हैं for the responses at the resonance पे जाकर क्या value आएगी at RD की, RV की, RA की. This value can be determined. Just आपको क्या चाहिए? Damping ratio चाहिए. बीटा और जीटा चाहिए, लेकिन रेजोनेंस पे बीटा 1 पुट कर दें. and you get this value. At resonance, beta is equal to 1. Like logarithmic decrement was used there in the free vibration where the force was not present. This diagram जो displacement response factor है, this is helpful in computing the damping zeta value. Damping ratio के लिए this is very helpful. How this is helpful? Because if you know difference जो एक frequency है, the difference of the frequency ratio on either side of the resonant frequency at which the amplitude is 1/2 times the resonant amplitude, तो वहाँ पे आपका for small damping RD आपको पता है the displacement response factor, RD is this one. So it is told that the resonance, the deformation response factor at the resonance is this one, 1/2 zeta, because beta is 1. उसका 1/2 अंडर रूट ले लें, मैक्सिमम रिस्पांस का 1/2 अंडर रूट. Draw the line. You get two values. One value on the left side, beta, इसको आप कह लें beta A, and the one side of this beta B A क्या कह लें, larger value, smaller beta A, क्योंकि horizontal पे क्या है beta. And when half power bandwidth, this is called, because you draw this line now and get the beta. So for half power bandwidth, what do you say? Taking this at resonance, 1/2 under root of zeta, resonant frequency का 1/2 under root, you will create it equal to 1 and solve for the zeta. Zeta के लिए solve करें and you get the answer as for smaller value of damping. जब damping small है, for smaller damping, generally the solution is like that, but for smaller value you get this solution, beta B minus beta A divided by 2. It means that damping can be determined for the damped system under the effect of force simply by two things. You need the displacement response factor RD, you have, and you need beta of that divided by 2. So you can determine the damping from this. This is also the application of the deformation response factor. So rotating machinery and eccentric mass vibrator, अगर आपका वो लगा हो तो फिर फोर्स चेंज हो जाएगी. Waiting in the lobby. For rotating machinery, it's like the PT जो है हम इसको ऐसे रिप्रेजेंट करते हैं ME ओमेगा स्क्वायर साइन ओमेगा टी. इसमें P नॉट नहीं होता, इसमें हमें चाहिए होता है मैस एक्सेंट्रिसिटी. जो मैस, क्योंकि रोटेटिंग एक्सेंट्रिक मास वाइब्रेशन होता है ना, मैस सेंटर से एक्सेंट्रिसिटी पे होता है, एंड ओमेगा स्क्वायर. So rotating machinery के लिए you need this all these parameters. ME omega square, this is a force response, and the response of the system for the rotating machinery is this one. It can be further simplified. So PT as a function of the time the rotating machinery is the response ये बनेगा. This is called an eccentric mass vibrator also. ये बिल्डिंग में कहीं अटैच करते हैं, फिर उसको रोटेट करते हैं एंड गेट द वाइब्रेशंस, और उससे आप काफ़ी पैरामीटर्स निकाल सकते हैं, स्टिफनेस एंड डैम्पिंग रेशियो, मैनी पैरामीटर्स कैन बी कंप्यूटेड. Then is the transmissibility, sports movement. कि आप अगर there is no force but sport is moving, it means that UG is in terms of sine omega t, or acceleration in terms of minus g omega squared, taking the second derivative. अगर ये हो तो then what will happen? Force तो zero है, but actually the acceleration, ground displacement and the acceleration is not zero. So you put the mass into acceleration, m into u plus ug, ug भी आप लें, put the values of the ug there, m ug, this one, and then pt जो है when it will ug जो है दूसरी तरफ जब मूव करेगा m ug, so this is actually pt, यानी कि equivalent force is not present but a value of mg omega squared sine omega t equivalent to the force is present. Yani if the force is not present but ground is moving, then this amount of force actually is present. So this is not zero. Ug, when it will go to the right hand side, it will become minus m g omega squared sine omega t. And then you can say that the response of the system in case of the ground motion is this one, and the value of the here g is basically this ground movement, g sine omega t. This how much is the p ground displacement, that is the g here. So ut can be represented in this form. When the ground is moving, this is the response of the system, and total response of the system will become ug plus u. ये ug है, ये u है, and the total response can be represented like this generally, where the gamma or amplitude जो है वो ground movement के केस में ये होगा, और tangent gamma, the phase angle will be this one. And what we see is that after the frequency ratio 2 under root, suddenly the amplitude ratio जो आप निकालते हैं, यानी कि ground movement का amplitude, the ground displacement and the amplitude of the motion, that suddenly change. I mean, it becomes zero at this value of the frequency ratio, and then it is reducing in this fashion. So ये है response of the system when you have the ground motion. इसके भी सारे expression दिए गए. ये transmissibility है कि what was the amplitude, what was the ratio between the amplitude of the total displacement क्या है और ग्राउंड डिस्प्लेसमेंट क्या है, इसको हम ट्रांसमिसिबिलिटी कहते हैं. कितना हमारा टोटल फोर्स थी, व्हाट वाज द अप्लाइड द रेशियो, हाउ मच इज ट्रांसफर टू द ग्राउंड में क्या था, एंड हाउ मच इज ट्रांसफर टू द बिल्डिंग. सिमिलरली फोर्स की भी होती है, फोर्स की भी ट्रांसमिशन होती है. द टोटल फोर्स ट्रांसमिटेड, ये जैसे आप कहते हैं कि ये फोर्स अप्लाइड है, हाउ मच फोर्स इज ट्रांसमिटेड टू द बेस पे कितनी शिफ्ट होती है. द टोटल फोर्स ट्रांसमिटेड टू द बेस इज सम ऑफ द फोर्सेस डैम्पिंग एंड द, दो हमने लेनी होती हैं, सम ऑफ द फोर्सेस ऑफ द डैम्पिंग एंड द स्टिफनेस. ओके, इन दोनों को सम करते हैं, एंड यू हैव द u वैल्यू, यू टेक द डेरिवेटिव ऑफ द u एंड पुट द वैल्यू. ये हमारे पास रिस्पॉन्स है ना फोर्स वाइब्रेशन का, और इसका डेरिवेटिव ले लें. So you can have the total Ft value. The total force transmitted to the ground is this one. इसको simplify करें. This is the total force. अब transmissibility क्या है कि ratio of the force which is transmitted to the ground to the base to the applied force, यानी कि Ft, the force which is transmitted to the base, ratio by the P naught, the applied loading. So this is the transmissibility. This is very important parameter. How it is very important parameter? कैसे है ये important? आप देख सकते हैं that how much force जो है वो हमने बिल्डिंग पे लगाई, कितनी ट्रांसमिट हो रही, and how much was applied loading, इसकी रेशियो निकलती. So you can also, ये जो ट्रांसमिसिबिलिटी था ये था कि कितना ग्राउंड एक्सेलरेशन, ग्राउंड मूवमेंट थी, कितना पीक डिस्प्लेसमेंट आया, एम्पलीट्यूड, how much is the ratio. So transmissibility ratio is basically an important factor, and you can get an idea कि कितने percent आ रहा है, and you can find out the values and adjust the beta or zeta so that this should not be going towards the resonance. So this was about the force transmission.